All right, let's dive into the pretty amazing world of measuring things that are incredibly, incredibly small. We're going to talk about a technique that lets scientists figure out the size of particles you could never, ever see with your own eyes.
I mean, that's the big question, right? It's a huge challenge for scientists who are creating everything from brand new medicines to next generation materials. Just think about it. The entire effectiveness of a drug or how strong a new material is can totally depend on the size of these tiny invisible particles. Yeah, we're talking about stuff like proteins, things that are thousands of times smaller than a single grain of sand. Being able to measure them is absolutely essential. But as you can imagine, getting an accurate number isn't exactly easy. You see, for a long time, the tools scientists had were, well, kind of clunky. Some would literally destroy the sample they were trying to measure. Others took forever to run, or, and this is a big one, they made scientists guess the particle's shape, which could throw the whole measurement way off. So clearly, they needed a better, more direct way to understand this invisible world. So to really get how the best technique for this works, let's start with a really simple analogy. I want you to picture one person trying to get through a super dense, constantly moving crowd. That person isn't walking in a straight line, are they? No way. They're getting bumped and nudged from all sides, which makes them kind of jitter and move around randomly. Well, a nanoparticle in a liquid does the exact same thing. It's constantly being bombarded by liquid molecules. This random dance has a name. It's called Brownian motion, and it is the key to everything. And what's so cool is how the size of that particle totally changes its dance moves. A smaller particle is just like a small, agile person in that crowd. They can change direction on a dime and zip around way faster. Those random bumps have a much bigger effect on them. But a larger particle, that's more like a big, lumbering person. It's got more inertia. The little bumps from the crowd don't really move it as much, so its movement is much, much slower. And that right there is the core principle. If we can just measure the speed of that random wiggle, we can figure out the particle's size. Simple as that.
So, how in the world do we actually measure this movement? Well, this is where a brilliant technique called dynamic light scattering, or DLS for short, comes into play. It's an incredibly clever way to watch that random dance without ever actually seeing the particles themselves. The instrument isn't taking a picture in the way we think of a photo. Instead, it shoots a laser right through the sample. As those particles jiggle their way through the beam, they scatter that light in all directions. A detector, sitting off to the side, doesn't see a steady glow. Nope. It sees a rapidly flickering or twinkling pattern. And here's the crucial part. The speed of that twinkling tells us exactly how fast the particles are jiggling around. Small, fast-moving particles, they create a really rapid, almost frantic twinkle. Big, slow-moving particles create a much slower, lazier change in the light. Okay, so we've got the twinkle speed. Now, how do we get from that information to an actual physical size? This is where some really beautiful physics comes into the picture. The software in the DLS instrument analyzes that twinkling pattern and spits out a value called the diffusion coefficient. All you need to know is that it's just a precise number for the particle's wiggle speed. A high number means a fast wiggle. The size we end up with is called the hydrodynamic radius. Now, this isn't just the physical size of the particle itself, it's what we call its effective size. That includes any little molecules that are stuck to its surface as it tumbles through the liquid. This is what we're really after, a solid measurement of how big the particle behaves in its natural environment. And the two are linked by the famous Stokes-Einstein equation. Don't worry, you don't need to know the math. You just need to get the relationship it describes. The diffusion coefficient and the hydrodynamic radius are inversely proportional. It's a beautifully simple idea. The faster a particle wiggles, the smaller its size must be. So why do we care so much about this effective size? Why go through all this trouble just to watch light twinkle? Well, it turns out it has massive implications for our health and safety, especially when it comes to medicine. DLS is an absolutely critical tool in developing modern medicines. It helps make sure that protein-based drugs, like antibodies, are stable and aren't clumping together. Because if they do clump up, it can make the drug useless, or even worse, cause a dangerous immune reaction in a patient. So DLS is essential for finding the perfect recipe to keep these medicines safe and effective. Check this out. Here is DLS in action with some real data for an antibody drug. Scientists use DLS to find the exact temperature where a drug starts to get unstable and clump up. They call this the onset temperature, or Tonsset. And at higher Tonsset is better. It means the drug is more robust. You can see right here that a pH of 5.5 is the sweet spot. That's where the drug is most stable, which is just vital information for making sure it works properly.
And this really is the bottom line. Because DLS is so fast and uses such a tiny amount of sample, it makes the whole development process way more efficient. Getting that precise data so quickly saves time, it saves money, and it helps get safer medicines to people faster. It's a win for everyone.
So that's the real power of this technique, isn't it? It takes this chaotic, random jiggle of particles, something that seems totally unpredictable, and turns it into a crystal clear, incredibly valuable measurement of size.
Dynamic light scattering really gives us this powerful lens to peer into a world we can't see. And it kind of makes you wonder, what other secrets are hiding in plain sight all around us, just waiting for us to shine the right light on them? Thanks for joining me for this explainer.